Exercise 8. Only 3 are left, including this one, in this set of exercises. So let us solve them. Once we finish these preliminaries, we can then go to proper number theory. So here we have to prove that this binomial coefficient 2n choose 2 for any positive integer n actually equals this expression. So this we will do by induction. We apply induction on n. When n is equal to 1, the left hand side of the given equation is 2 times 1 choose 1, which is 2, and the right hand side is in the numerator there will be only one factor, because if we put n equal to 1 here we get 1, and in the denominator also there is only one factor, which is 2. So 1 over 2 times 2 square. So this is also equal to 2. So the given equation is true when n is equal to 1. Now we assume the induction hypothesis. Assume that 2n choose n equals that expression divided by 2 times 4 times 6, all the even integers, times 2 to the power 2n for some positive integer. Some positive integer n. Then let us start with the right hand side of the equation when we have n plus 1 in place of n, and we will see that it will become equal to the left hand side. N plus 1. If we consider another factor, the next odd integer will be 2n plus 1. Like that, in the denominator where we have even integers, the next one will be 2n plus 2 times, here if we have n plus 1 in place of n, then we have 2n plus 2. So this is the right hand side when we have n plus 1 in place of n. Okay, now clearly this can be written as a product of two expressions, 2n minus 1 divided by 2, 4, 6, etc. 2n times 2 to the power 2n. This is one thing, and whatever we haven't written, 2 square times 2n plus 1 divided by 2n plus 2. Now this, of course, here we can use the induction hypothesis, and in its place we can write 2n choose n, and here we can cancel 1 2 and write 2 times 2n plus 1 divided by n plus 1. Now we use the definition of this binomial coefficient. 2n factorial divided by n factorial times 2n minus n factorial times this. Okay. Now 2n factorial divided by n factorial times n factorial. Let us write all the things together. Times 2 times 2n plus 1 divided by n plus 1. Okay, now what we do, what do we need actually? To get the left hand side, we need 2n plus 2 choose n plus 1. So that means we will need 2n plus 2 factorial. We have only 2n factorial. We need two extra factors, 2n plus 1 and 2n plus 2. 2n plus 1 also is there for us, but 2n plus 2 we don't have. We have one single 2. So if we multiply and divide by n plus 1, then our job will be done. At least we will get 2n plus 2 factorial. So let us do that. 2n factorial times, I can write like this, 2n plus 2 times 2n plus 1 divided by n factorial times n factorial times n plus 1 square. So what we have done, we have multiplied and divided by n plus 1, and that n plus 1 in the numerator, we have multiplied that by this 2, and here we have 2n plus 2. Okay, so now the numerator is okay. The numerator now becomes 2n plus 2 factorial. And what about the denominator? In the denominator, what we do, we take an n plus 1 with n factorial and write n plus 1 factorial. We can do that once more because we have another n plus 1 and n factorial available. So n plus 1 factorial. Okay, now this can be written as 2n plus 2 factorial divided by n plus 1 factorial. Now see this, 2n plus 2 minus n plus 1 factorial. This ultimately becomes n plus 1, and this expression is nothing but this binomial coefficient. that is 2 times n plus 1, choose n plus 1. So this completes the induction, because now we have the left hand side of that equation if we have n plus 1 in place of n. So this completes the induction. Next, exercise 9. Establish the inequality. When choose n is less than 2 to the power 2n for any integer n strictly greater than 1, and there is a hint also. Put x equal to 2, 4, 6, etc. up to 2n. Comma y equal to 1, 3, 5 up to 2n minus 1, and z equal to this. Show that x is greater than y and y is greater than z. Yes. This is one thing, and hence x square is greater than xy, which is greater than xz. This somehow will help us prove these inequalities. Okay, so let us proceed accordingly. Note that here n does not start from 1. The smallest possible value of n is 2. So for n greater than or equal to 2, define xn to be this, the product of these even integers, even positive integers, and yn to be that such a product but of odd positive integers. The reason we are using suffixes here is that it shows that xn and yn are changing. It's not a fixed thing, it changes with n. Okay. Actually, we are just following the hint, but we haven't defined z because z is nothing but n factorial, so there is no need to define it separately. We now show that xn is strictly greater than yn, which is greater than n factorial, for all n greater than or equal to 2, obviously. For this, we apply induction on n, keeping in mind that now the base case is when n is 2. We have, so in that case we can actually calculate the values. x2 will be what? When n is 2, we have 4 here, so that means 2 times 4, this is 8, and that is greater than y2. If we put 2 here, then we will have 3, that is 1 times 3, which is 3, and this is clearly greater than 2 factorial, which is 2. So that is our basis for induction. Now assume that xn is greater than yn, which is greater than n factorial, for some integer n greater than or equal to 2. This is our induction hypothesis. Then what is xn plus 1? Xn plus 1 will be this 2, 4, 6, etc. 2n times 2n plus 2. That means this is equal to xn times 2n plus 2. And now this will be greater than yn times 2n plus 1. Why? Because 2n plus 2, this is 2, okay. 2n plus 2 is greater than 2n plus 1, and xn is greater than yn, that is our induction hypothesis, and all the numbers involved are positive integers. So we have this inequality. Okay, now yn times this means what? 1, 3, 5, etc. 2n minus 1 times 2n plus 1, and that is nothing but yn plus 1. That is equal to yn plus 1. Okay, and how are these things greater? Oh, okay, yes. Now note that yn by the induction hypothesis is greater than n factorial, and we have 2n plus 1 along with yn, they are multiplied. So yn is greater than n factorial and 2n plus 1 is greater than n plus 1. So this will be, actually this expression is greater than n factorial. N factorial is greater than yn, less than yn, and n plus 1 is less than 2n plus 1, and this is n plus 1 factorial. So xn plus 1 is greater than yn plus 1, which is greater than n plus 1 factorial. This completes the induction. And so this inequality that we wanted to show it has been shown to be true. We can now use this inequality to actually get what we want, the inequalities that have been given in the exercise. Okay, so we start with this thing. 2 to the power 2n times n factorial square will be what? If we look at the expression for xn, if we look at the definition of xn, you can see that since all the factors are even integers, so from each one of them we can take 2 common out, like this. From this we get 1, 2, from here we get another 2. So how many factors are there? N factors, 2 times 1, 2 times 2, like that up to 2 times n. So we will get n number of 2's. So that becomes 2 to the power n. And after taking things common out, we are left with this. That means 2 to the power n times n factorial. If you square this, then you get this, that is so that means this is xn square. Okay. Now xn square, because xn is greater than yn and xn is a positive integer, so if we multiply on both sides of this inequality by xn, on the left hand side we will get xn square, on the right hand side we will get xn yn. Now if one multiplies xn yn, what does one get? Times 1, 3, 5. In the first factor, we get all the positive even integers less than or equal to 2n. In the second factor, we get all positive odd integers less than or equal to 2n. In other words, we are actually getting this. That is nothing but 2n factorial. Okay, so this is 2n factorial, x and yn, but because yn is greater than n factorial, we can multiply both sides of this second inequality by xn and get xn yn greater than xn times n factorial. This we can get. Now what is xn times n factorial? Xn is of course this, so we are getting one n factorial extra, So this along with n factorial will give us 2n times n factorial square. So we get inequalities like this. This implies okay, it will be somewhat better if we write just the inequalities before drawing any conclusion. That is 2 to the power 2n times n factorial is greater than 2n factorial, which is greater than 2 to the power n times n factorial. This implies, now if we divide throughout by n factorial, which we can do because n factorial is positive, then we get now since 2n choose n is equal to 2n factorial divided by n factorial times 2n minus n factorial, which is equal to 2n factorial. This will also be n factorial, so we have n factorial square. So we finally have the inequalities that we were seeking. An upper bound and a lower bound for this, or the value of this binomial coefficient. So this completes the solution. And finally we have this exercise 10. The Catalan numbers. Defined by this formula 1 over n plus 1 times 2n choose n. And which becomes equal to 2n factorial divided by n factorial times n plus 1 factorial. We know why this happens because this is the binomial coefficient we have already obtained here. So we have this. Now if you combine the n plus 1 factor with one of the n factorials, then you get n plus 1 factorial. The other n factorial stays as it is. For non-negative integer, okay, does it make sense if we take n equal to 0? in terms of the formula for the binomial coefficient, it makes sense. That is, I am a little bit concerned about the case n equal to 0. Have we defined anything like this? If we just simply follow the formula, then there is no problem, because we have only 0 factorial. So ultimately we get 1. Okay, so that is the case when n is 0, then C naught is 1. Fine. So that means n is any non-negative integer. They form the sequence one, 1, 2, 5, 14. A few of the beginning terms of this sequence are given here: 429, 1430, 4862, and so on. They first appeared when Eugene Catalan these are the years of his life, from 1814 to 1894, showed that there are Cn ways, Cn number of ways of parenthesizing a non-associative product of n plus 1 factors. I need ink. Give me a moment. Of n plus 1 factors. Non-associativity is something which does not occur as frequently in mathematics as non-commutativity. An operation is a binary operation is commutative, which some of you already know, when the order in which you compose two elements does not matter. If AB is equal to BA, which is the case for ordinary addition and multiplication, then the operation is called commutative, which ordinary multiplication and addition are. A non-commutative operation is, for example, function composition. When we can compose two functions in two different ways, when both of the compositions make sense, then it's not necessary that f composition g and g composition f are equal. That is not always the case. In general, they are not equal. Just like that, matrix multiplication is also non-commutative, but non-associativity is something else entirely. Non-associativity means that the operation is not associative. This is not necessarily equal to this. If I am remembering the things correctly, I think cross product of vectors is non-associative. Let us just see one situation. Okay, you know about these unit vectors I cap, j cap and k cap. Now what happens when we, okay, shall we get anything? If yes, we can take cross product like this. What happens when we calculate this cross product? I cross j is k, and k cross k is 0. Okay, now what about I cross j cross k? J cross k is minus, no, this will not give me non-associative. Oh, why should I go that far? There is a much simpler non-associative operation. Ordinary subtraction, we don't even have to consider real numbers. We can consider just natural numbers. So this is A, this is B and this is C, and we have the operation in between any two natural numbers. This is however not an operation on the set of natural numbers in the ordinary sense of a binary operation, because when we consider subtraction, we don't remain necessarily in the set of natural numbers. For example, 1 minus 2, where 1 and 2 are natural, is itself not a natural number. So instead we can think of this as a binary. It is a binary operation on the set of integers, which has all the positive, all the negative integers. So there is no problem when we take the set of integers. Okay, this is equal to minus 2, but what about this? One minus 2 is minus 1, so that minus 1 and this minus, that will give us plus 1, so 1 plus 1 is 2. So these two things are not equal. So it's not necessary that AB times C must always be equal to A times BC. It may not be. So that means when we are dealing with a non-associative operation, it matters how we are calculating the product. We first multiply A with B, and when with that result we multiply C. Multiply I am saying because we have written it in this way. And if we do this one, if we calculate this one, you take the product of A with BC, then you will most likely get an entirely different result. Now a natural question occurs, fine, so if I have 3 factors, in how many ways can I parenthesize such an expression, such a product? This is one way, this is another way. Is there any other way? So that number turns out to be Cn, and it was shown by this fellow Catalan that there are C1 ways of parenthesizing a non-associative product of n plus 1 factors. For example, I think an example is also given here. For instance, when n is equal to 3, so the case that we were considering just now, when n is 3, then n plus 1 factors, not that case, okay, there are 4 factors, one more than what we consider. Then there are 5 ways, and these are the 5 ways: A, B, C, D. Then A, B, C, D, A, B, C, D, A, B, C, D. When we are bracketing a product and we want to know how many ways this can be done, note that we are not changing the order of the factors at the same time. ABCD remains ABCD. And one more is this. Okay, now what is it that we have to do here? There you can in fact okay, let us just verify that this number 5 is actually given by Cn. What happens when we calculate C3? It is 1 over 4 times 6 choose 2, which is 1 over 4. After using the definition and cancellation, we will have 6 times 5 divided by 2. Is it correct? What we have here? Oh, 3. What the hell? This is 3. I am putting n equal to 3. So that means that this will be 3 times 2. Yes, we get 5. Okay. So C3 is 5. So there are 5 ways of parenthesizing a non-associative product of 4 factors. Now the exercise asks this: for n greater than or equal to 1, prove that Cn can be given inductively. by this inductively or recursively by this relation. Cn equal to 2 times 2n minus 1 divided by n plus 1 times Cn minus 1. The exercise isn't anything very difficult or very non-trivial, but the numbers are interesting, and it also tells us about Catalan numbers, which I don't think you will come across this anywhere else other than in some such exercises. Maybe there is something else also on Catalan numbers, I don't know. So let us see the solution. Like this, we will also come across many other different types of numbers, specifically prime numbers, Fermat primes, things like that. Okay, so since we have a formula for Cn, we can directly use that formula. So it's better to start with the right hand side. It's not always a good idea to start proving any such thing with induction. Sometimes a non-induction proof is also good. Okay. Now we can directly use this expression. 2 times n minus 1, that means 2n minus 2 factorial divided by n minus 1 factorial divide O. So this will be n factorial. Okay. Now we have to think of Cn plus 1. Cn plus 1 according to this formula is 2n plus 2 factorial divided by n plus 1 factorial times n plus 2 factorial. So we need 2n plus 2 in the okay. We need this one and this one together, they will give us 2n minus 1 factorial, but we need 2n plus 2 factorial. So we need to multiply this by 2n plus 1 and 2n plus 2. What happens in the denominator? In the denominator, we need n plus 1 factorial, which we will get by combining this n plus 1 and n factorial. And we have n minus 1 factorial. Now since we have multiplied by these factors, we also have to divide by them. 2n plus 1 times 2n plus 2. Okay. So now this 2 and this 2, they will cancel each other. In the numerator we have what we want, 2n plus 2 factorial, at the cost of bringing this many things in the denominator. But let us see what happens. This we will not touch because we need this. N minus 1 factorial times n, okay, times Actually we can cancel two, no, we cannot do that, because we cannot cancel this 2 with this 2 here, because we need this 2n to make 2n plus 2 factorial. Okay, fine. So we have to keep it like that only, but we do need n plus 2 in the denominator. Also, at the same time, what shall we do with this 2n plus 1 and 2n plus 2? Two n plus 1 and 2n plus 2. Have I made a mistake somewhere in maybe taking this down? It is clearly written as Cn and Cn minus 1. Okay. Cn plus 1. The formula for Cn is also correct, because we have already calculated C3 equals 5. So there we don't have any mistake. Maybe I'm missing something obvious here, or I messed up here. Let me see. Cn minus 1 is going to be 2n minus 2 factorial divided by n minus 1 times n. Okay. In the denominator we need, besides n plus 1 factorial, we need n plus 2 factorial. Okay. From here I am getting n factorial. So I need n plus 1 and then n plus, how shall I possibly get n plus 2 keeping the numerator equal to this? That I don't see. Or instead of approaching the problem like this, let me just see if I can salvage it this way. What I am going to do is, I am going to calculate this quotient. Directly and see what happens. If this thing comes, fine, we have to do it carefully. If this thing does not come, then maybe I have taken the exercise down incorrectly, or maybe there is an error. Let me also see this part. 2n factorial. Okay, no, there is no problem with this. Okay, fine. Let us hope for the best and jump right into it. Divided by 2 times n minus 1, so that means 2n minus 2 factorial divided by n minus 1 factorial times n factorial. Okay, so we now have 2n factorial times n minus 1 factorial times n factorial divided by 2n minus 2 factorial times n factorial times n plus 1 factorial. Okay, so these two things cancel each other immediately. Now this can be written as this, and let us keep n minus 1 factorial as it is. In the denominator we have 2n minus 2 factorial. Now we can decompose this one. N plus 1 into n times n minus 1 factorial. So the factorials now all get cancelled, and we are left with what? This n and this n, they get cancelled, so we are getting what we need, no? 2 times 2n minus 1, we don't have anything else in the numerator. In the denominator we have n plus, okay, so that's what we wanted. So that means the other approach, I made some mistake there. Okay, I was not getting something which I should have got. That is just the solution. You can multiply both sides by cn minus 1 since it's going to be a positive integer, and you can get the given relation, recursive relation. So this completes this set of exercises. After this there is one more section. It's a little bit of history on early number theory. That section also has its own exercises. So I will briefly go through the history, and then we will solve those few exercises, and then the preliminaries will be over, after which we can again go to actual number theory, proper number theory. So with this I end this, I can't say short video because I don't know how long this video has been, but because of this mess ups, I think I took much longer than what I was preparing for. Anyway, so that will be all for number theory. So see you in the next video. Until then, it's me, Lucifer, from a mathematical room. Have a nice night.